Thank you, Lillian, very much for the introduction. Thank you for the invitation as well. It's one of these sort of serendipitous links that um, I have with your colleague Marielle through one of the journals I edit, a journal called Antarctic Science. Um, yes, I am in the wrong end of the world from most of you. But what I'm hoping with this presentation and the discussion afterwards is to see if we can do something that's happening increasingly in the polar research community, which is drawing parallels between what goes on in various disciplines and in various applied areas between the two polar regions. So overall, I want to talk about the future of conservation strategy in Antarctica. It'll start fairly dry. I'll give you what I'm going to try and talk about as background, sort of feed the discussion, is give a brief background on conservation practice, which basically means area protection in Antarctica, and how things worthy of protection are identified. I'm going to give a very brief introduction to Antarctic terrestrial biogeography. That sounds somewhat scientific-ese, but basically patterns in what occurs where. Looking at Antarctica from a long way away, very tempting to think of it as one big icy continent. If you start looking at it in terms of the way that biodiversity is distributed, very quickly realize it's much more complex than that. I'm going to flag various features of the current protection system that's in place in Antarctica and in the context of the way the Antarctic Treaty legislates and governs Antarctica. And I'm going to then throw a few examples up. I'm not going to talk about them in great detail, but examples of the sort of information or the sort of practices we have available to us that could improve the future application of conservation policy in Antarctica. So to give a bit of background to the Antarctic, if people are not particularly familiar about it, obviously Antarctica is a big continent. It's about twice the size of Australia. It's a very isolated continent. And until, in reality, the early part of the 20th century, the exploring era, and then from sort of the mid-century onwards, which we can say is the sort of scientific era, Antarctica basically had no human contact. It's an isolated continent, no native human population ever. Since 1961, it's been governed by the Antarctic Treaty, and that's a treaty that was negotiated in response to the success of something called the International Geophysical Year back in 1957-58. Particularly topical at the moment, it's worth being aware that it was negotiated at the height of the Cold War, yet key parties of the treaty are the United States and what is now Russia, what was then the Soviet Union. One of the early examples of science cooperation transcending an awful lot of very nasty international politics. In terms of environmental protection, under the treaty, there is legislation, international agreements in place, in effect, that controls how conservation takes place in the Antarctic, called the Protocol of Environmental Protection to the Antarctic Treaty. That came into force in 1998. It was negotiated in 1991. And in the marine environment, the Convention on Conservation of Antarctic Marine Living Resources, known as the CAMLAR Convention. Practically, across Antarctica, there are currently a bit over 70 largely terrestrial protected areas in Antarctica. Now, you can think about those in terms of national parks, nature reserves, SSSIs, but various sort of names given to them in different parts of the world or different countries. Not all of those areas are protected for biodiversity values. I'll come back briefly to that. There are only 2 marine protected areas in Antarctica currently, one around the South Orkney Islands and the South Atlantic, and one in the Ross Sea, a long way south of New Zealand. In practical terms, areas to be protected have to be proposed in the treaty system, and the proponent, the proposing party, and that means country, manages ASPA's protected areas that they propose. Now, I'm not going to give a big background to the Antarctic Treaty, but it is a big international treaty. It originally had 12 signatory nations back in 1961. There are now, I think, 54 signatory nations. It's one of these international treaties that countries can join. It's separate to the United Nations. It's not a treaty under the UN. Of those 54, 29 countries are so-called consultative parties, and that is a status of membership that actually gives them decision-making power in the treaty system. Bringing them back to ASPA, about half of the consultative parties, 15, are responsible for proposing and managing existing protected areas. So that's the extent of area protection. Various ways of expressing that. I'm going to illustrate that in a second. There are things other than biodiversity that can be protected. There are sites designated for their geology, sites designated for their historical importance. And at a slightly larger scale, there are things called Antarctic specially managed areas, which basically are designed to manage operations in areas where multiple countries operate, multiple activities take place. So they're not the same status as protected areas. What is worthy of protection? The Antarctic Treaty calls these values. I'm not going to read all the words on this slide, but basically the treaty wording has a pretty general range of so-called values that may be used to justify the proposing of an area for protection. That's the first bullet. The second bullet, more specifically relevant to biodiversity protection or biology or ecosystem protection. And the treaty wording, or the environmental protocol wording, includes specific sets of words, as illustrated here, to define the sort of things that are likely to be, are justifiable to be protected. Things, areas that are inviolate, have never been visited or disturbed. An important one is representative examples, ... Some people would say all of Antarctica is protected to some extent by its isolation. But within that, the area protection system is intended to protect representative examples of the ecosystems that exist in the region. And a number of other specific named values are used for this purpose. Now, that all sounds fine. But then if we look at all of Antarctica, as I said at the start, there is a natural tendency to think about it because it's so far away and we've only been getting to know it for the last 6-7 decades. There's a natural tendency to assume that it is all one thing. Like all Antarctic ecosystems are subsets of the same type of ecosystem. That, and only the last 10 to 15 years, we've realized that that is actually a very incorrect way of looking at Antarctic biodiversity. This map slide basically gives a summary of our current view of Antarctic biodiversity and biogeography. The take-home point from it is that lots of parts of Antarctica, in terrestrial terms, are unique, are distinct from each other. So these things called ACBRs, they're known as Antarctic Conservation Biogeographic Regions. And based on a combination analysis of physical, geological, climatic, biological, and ecosystem features, these areas are distinct from each other. And they're as distinct from each other as any of them are from subantarctic ecosystems or Southern South American ecosystems and so on. This highlights that Antarctica has a very complex evolutionary history and a very long-term evolutionary history. So Antarctic biology, sorry, in that. But that is another story which great fun to expand on, but it doesn't particularly relate to the subject of this talk. It does lead on to some immediate comments about that representation point from the earlier slide. So the basic panels on this slide all look at parts of the overall map of Antarctica, and they're all again coloring the different ACBRs in different colors. We then have a series of white dots, which are indications of major areas of human infrastructure or activity. You'll see some of them are right in the middle of the ice sheet. They're not relevant to the terrestrial debate, but they are operational areas. And then the blue dots are the current distribution of those 72 protected areas that I listed on an earlier slide. Without going into all the detail here, the take-home point here is that those ASPAs are not distributed in a representative way around the continent. Many of the so-called protected, so-called biogeographic regions, the colored bits, don't have any ASPAs at all. They don't have any formal protection at all. Others have a great density of ASPAs, generally because they're close to active research stations. And this is particularly true in Victoria Land. If you can see my pointer down here in Victoria Land, and also in particularly the northern Antarctic Peninsula and the South Shetland Islands. So immediately we get a first inclination that area protection in Antarctica is not representative of what is in Antarctica. Now, that leads us to a number of other concerns or a number of other weaknesses that have now been identified in the current ASPER system. And bearing in mind that this system developed over the last 50, 60, 70 years, some of what we now know wasn't known at the start of this development. However, a couple of key features or key important weaknesses in the current system is that simply counting the number of ASPERs, number of protected areas, is not really a very productive way of seeing how effective they are. One feature of them in the right-hand panel here, most current protected areas are small to very small. Most of them are in immediate contact with non-protected ice-free ground, and most of them are very close to centres of human activity. By that, I tend to mean research station areas or highly visited tourist areas. Overall, this presents quite a few practical challenges in terms of you can define an area, but how do you stop things entering it? How do you stop them becoming contaminated? How do you regulate this? And the simple fact that most of these protected areas are simply not large enough, that's either in big geographical extent or altitudinal range, to be resilient to the climate change trends that we all know now are affecting polar regions very strongly. As an example of how unrepresentative they are, I'm going to pick on vegetation here. The purpose of this slide is focusing on vegetation. First of all, those 72 ASPERs protect less than 1.5% of the overall ice-free area in Antarctica. And there isn't very much ice-free area in Antarctica as a whole. It's about 25,000 kilometers squared. Most of the continent is permanently covered by ice. That is far less than the often quoted HE targets in the Kyoto Protocol. On land, the target there is around about 17%. Now, that has been modified in the most recent update to the protocol. But the bottom line is that we're actually protecting about less than 10% of the intended target area that the world's conservation bodies do reckon is appropriate. And the other conclusion here is that Antarctica is no better protected than any other part of the world in terms of this form of protection. If we look at vegetation, because it's visible, as a proxy for biodiversity, because things live in it, it's quite a good proxy measure of identifying important terrestrial biodiversity areas, important assemblages. If we do that, then in all of Antarctica, the total amount of vegetation protected is about 16 square kilometers. And as indicated by this figure, you don't need to worry too much about details on these figures. Half of that vegetation, this point up here at the top right, so half of that 16 kilometers squared is present in one single protected area. So you could argue pretty rapidly from this that biodiversity protection is not representative in the ASPER system. As a side thought, this is one point that I think is also relevant up in the north as well. While we have a natural tendency to focus on the richest ecosystems in a given part of the world, the ones with the best vegetation, the ones with the biggest number of birds or whatever else, in much of the polar regions, ecosystems that are representative are often pretty barren and low diversity. And we have to have that in consideration in our mechanisms of choice of area protection. There are some changes over time in the treaty system. There was a historical tendency to declare ASPERs basically sort of cherry-pick good areas near to research stations, which were the favourite research sites of particular researchers early in the treaty. These days, ASPERs are being designated further away from stations in more remote areas. There is a move towards away from single-party proposals, so single nations proposing their favourite ASPER, to multi-party proposals, selecting ASPERs based on real scientific rationales. Both of those are positive changes. Having said that, if you look at the N values at the top of the columns, the rate of ASPER designation has halved in the past 10 years, and this is a trend that does seem to be continuing at the moment. Bearing in mind that protection in Antarctica is a long way short of the global intention, that can't simply be explained by saying enough area is already protected. So an overall conclusion of this is that the current system has developed in a very uncoordinated manner, an ad hoc fashion effectively, and it is undeniable that it today results in conservation values being very poorly represented, very unevenly represented, and in that the area protection system predates the current recognition of conservation biogeographic regions. It really does not represent or recognize the different elements of biodiversity represented across all of Antarctic biogeography. There are some improvements. There are a number of ways this situation could get better very easily and very rapidly. There are some large-scale future developments that are relevant, and this will be relevant well beyond the Antarctic region on its own. Most people are aware of IUCN red data books listing most endangered species and so on. The IUCN is also developing a red listing process for entire ecosystems. So the intention is to produce a red list of ecosystems globally. With the IUCN, this is intentionally a global process. Neither species nor ecosystem red listing has yet been properly applied to, I think, either the Antarctic or the Arctic, to be honest. Within Antarctica itself, this is mentioning a specific SCAR initiative, something called ANTOS. One of the things that we need to know if we are to define conservation areas is baseline data. And ANTOS is an international initiative increasingly becoming active now that intends to provide a biologically relevant and continent-wide network of environmental monitoring. In other words, ability to describe the environment and how it might change. Completely separate potential future contribution is that of citizen science. This is really high profile in both the scientific and the community interest parts of the world. It hasn't received an awful lot of application in the polar regions, partly because of the practicality of getting to many of them, partly because of the costs involved. But citizen science provides a potentially very good source of data, very good source of community involvement as well, where you have communities living in polar regions. And as I did mention briefly, I don't really want to build on the last point here. There are already systems in place for quantifying non-living, non-biology, biodiversity-related values such as geology, geoconservation, and history. Right. In terms of data availability, as in many fields, in the Antarctic, this is increasing rapidly. There is a thing called the SCAR Biodiversity Database, available via the SCAR website, that gives the most up-to-date knowledge available of georeferenced biodiversity data. Plainly important in conservation terms. Having said that, and this applies to both polar regions, most Antarctic terrestrial diversity is small, cryptic, not very visible, and requires specialist knowledge. So the evenness of baseline survey available is extremely variable, and this continues to be a major challenge. It's not the sort of thing that is easy to visualize being surveyed remotely by some sort of automated process. Those of you who are biologists or aware of molecular biology approaches will be aware that these do offer tools to rapidly improve knowledge of biodiversity, with caveats within the techniques as well. But there are scientific advances that do improve our ability to carry out survey work. There are a whole range of potential data sources that can be incorporated in modeling approaches, assessment approaches to identify vulnerable areas or areas worthy of protection. One example, things called important bird areas. This is a map that shows the identified ones in the Antarctic. The same are available for countries worldwide. If we look at the distribution of marine vertebrates, anybody who's been near a large bird colony will be very aware that you can smell that colony from a long way away. That is an indicator of it being a source of fertilization for the terrestrial environment. Generally speaking, ammonia or nitrogen related is what you're smelling. This is a map that shows the potential influence of marine vertebrate breeding colony locations on terrestrial diversity in the Antarctic Peninsula. That sounds like a very specific subject. The point is that marine vertebrate concentrations provide a proxy for identifying richness in terrestrial biodiversity. So even where we can't survey that biodiversity remotely by normal means, we can find indicators that help us predict where that biodiversity is. This is an approach that can be applied far more widely in the Antarctic Peninsula. Complex multivariate analyses, that doesn't look obvious from the title of this slide, are becoming increasingly available, where combinations of geological, climatic, weather, ice cover, ice melt, biodiversity, morphology, and so on data, so-called layers in spatial models, are combined to try and identify areas that have comparable types of habitat. The map is an example of trying to apply that across the entire Antarctic. But in principle, you can use a means to define the characteristics of different habitats, and you can then look in very large-scale spatial data sets to draw together areas that are likely to have similar features. And I sort of cast doubt on remote sensing earlier on, in the sense of there are challenges to its application in the polar regions, but there are improvements, and quite rapid improvements, in the ability, the resolution of remote sensing. So if we look in terms of vegetation, the increasing availability of what are called hyper and multispectral satellite recording is a major contribution to identifying different vegetation types, as is the progressive reduction in what's called the pixel size, if you like, the photograph size that satellite platforms can achieve. So very well-known things like Landsat, you're looking at pixel sizes of several hundred meters squared sometimes, certainly several tens of meters squared. Some of the most recent satellites, we're now looking at pixel sizes that come down to a proportion of a single meter squared, much more relevant to the sort of biology that you see across much of the higher Arctic regions, Antarctic regions, and so on. So it starts to become practical. It still requires, the use of this methodology still requires ground truthing. And one of the biggest challenges still remaining is to what extent we can resolve individual species or even individual vegetation types within the data that these approaches produce. So this is an ongoing story. It's certainly not a completed story. If we have that problem with vegetation types, we have an even greater problem with microbial communities. And microbial communities are one of the sort of black holes of knowledge of most ecosystems. There is a statement that all ecosystem processes depend on microbes, but it is very, very, very difficult to identify a robust means of surveying microbial communities. There are certain types of microbial communities, and many of these are dominant in both polar regions, that are visible in remote sensing approaches. Now, these two slightly odd-looking figures basically are looking at snow algae, which are microbes that develop in the snowpack in the summer, and they turn snow from being white to being yellow, pink, green, those colors usually. The left-hand image is the actual photograph. The right-hand image is an analyzed version of that, which is essentially trying to assess the distribution of different types of snow algae within areas of snow where they're growing. And it demonstrates that microbial communities of some sorts can be resolved this way. That seems like a very small point. Given the extent of microbial communities in the polar regions, it's actually a very important point. Something else we all know, polar regions are facing rapid climate change. I'm not going to go into that in vast detail. There is a feature known as polar amplification, which both confirms through existing data and predicts in the future that warming processes will be accelerated at higher latitudes in both hemispheres. In terms of biology, one of the most important consequences of this is what is illustrated here, and that is that warming leads to paleontology, snow and ice melt, and predictions of increased ice-free area, various linked predictions associated with that. The scale of that is perhaps one of the more alarming things. I mean, at a global scale, it is already well predicted that in maybe as little as 20 to 50 years, that lower latitude montane glaciers will be lost. The tropical glaciers are dying, basically, and they will not be replaced. This map is taken from a paper that concludes the business as usual scenario of warming. So what's going on at the moment will lead to an approximate tripling of ice-free area on the Antarctic Peninsula. For the whole continent, that comes down to about a 25% increase, but that's still quite a big increase over the next 70, 80 years. This obviously has implications for future distributions, both of native and non-native invading species that come in. A couple of examples of the latter, and I'm going to whiz through this one, but this is an example for a native species, currently occurs only on the South Shetland Islands, over here, west of the Antarctic Peninsula. And under by 2050, on the business as usual scenario, it's predicted it could occupy, say, more or less the entire Antarctic Peninsula. It could progress quite a long way south. By 2100, it could actually occupy the entire Antarctic Peninsula. And interestingly, you don't need to know the map details, certain parts of the continental coastline will become suitable for it. Very unlikely to disperse there of its own accord, much more likely, since it can fly, to be able to disperse down here. But that leads on to a question I'm going to finish with what is the human influence on this? We can do the same sort of analyses on species that are currently invasive in Antarctica. There aren't many, but there are one or two. The number here is a wingless fly, established in one particular set of islands in the Antarctic. Actually, current distribution is within this sort of black limit here, if you can see where the arrow thing. The red and yellow colors indicate the current establishment risk, even under today's conditions, never mind under conditions as they will change over the next century. So plainly, it could occupy a far bigger space on the islands it's already established on than it does yet. This is an active colonization event. Same species, similar sort of modeling, the entire Antarctic Peninsula. The actual islands introduced to right up here, just off the map. But over the next century, this predicts that the ground being high risk could occupy most of the western Antarctic Peninsula. And there's a species that is pre-adapted to live in the sort of habitats in this region. The final point then I wanted to make is to pick up on the idea of humans having an important role here. Now, this again looks like a complex slide, but the take-home point is very simple. This left-hand panel goes back and it looks at a typical location in each of the conservation biogeographic regions. And the point and the bar in each column is an idea of the simple annual temperature variation, mean and annual temperature variation at that location. The take-home point on the left-hand side here is that many of these ACBRs, not all of them, but many of them, overlap extensively in their environmental conditions. Implicitly, that says that if you can survive in one of them, if you get moved to another one, you can survive in that as well. This map, and there are far more complex versions of this map on the right available, indicates different ways that national operators, not even thinking about the tourist industry, national operators move between different stations and different regions of the Antarctic. And again, the take-home here is simple, is that most parts of the Antarctic are connected to somewhere else, to another biogeographic region, maybe very extensively, all the way around the continent, maybe within part of the continent. But the human connection is already there. This highlights that we potentially play a very important role in moving things around in the Antarctic. So, to put all that together, it's safe to say our current protected area system in the Antarctic is imperfect in many ways. Having said that, it's also reasonable to say that the magnitude of existing threats and the damage that has already happened are actually very limited. Therefore, the need for effective and representative strategies of protection is timely. It is an appropriate thing to be considering. And on that basis, these are actually one of the highest priority measures of the ATCM at the moment. One of the plus points is that the Antarctic Treaty, and particularly what's called the Environmental Protocol, means that the governance mechanisms are in place and actually relatively simple to apply. What it requires is the will to do this from the parties concerned. It doesn't have to develop the system in the first place. It is increasingly clear that human activity and its associated consequences is central to either the potential damage or the potential safety in the future of Antarctic ecosystems, particularly through our role in changing distributions, moving species around to places where they don't naturally occur. And to achieve this, when actually it's not rocket science, adherence to effective biosecurity is vital. And there are many tools, many sources of data, strategic approaches to conservation planning and so on, that are available that provide us with the opportunity to develop this scientifically robust, representative, and continent-wide protection system. So I'll stop at that point. It actually did take slightly longer than I intended, so sorry about that. I will stop there and leave it up to you to lead on from here.
Thank you very much, Peter. As someone who is interested in Antarctica, but not a scientist myself, this was really fascinating. And I want to open up the chance for questions to the floor now, but if it's okay, I think I'd like to start off with a question of my own. And so one of the things that I was thinking about during your talk was about tourism, because you briefly mentioned tourism, and I'm thinking about how interest in Arctic tourism is increasing, especially in Greenland, in and around Greenland. And so thinking about Antarctic tourism as well, what are your thoughts, or what are the thoughts of Antarctic scientists on the effects or on the implications of increasing tourism to the Antarctic region?
It's a very fair question, although that could be a whole separate talk subject. I have very close interactions with various parts of the Antarctic tourism industry. Perhaps one thing to say at the outset, so Antarctic tourism is pretty well regulated. There's a thing called the International Association of Antarctic Tour Operators, IATO. And there is an Arctic equivalent, and many of the Antarctic tour operators obviously work up in the Arctic in the down season in the Antarctic. Now, the tourism industry, in reality, I think is very aware that it runs the risk of being the thing that kills the goose that lays the golden egg. If it damages its ecosystems, if it damages its targets, then it stands to lose out. So in many respects, the Antarctic tourism industry has been ahead of most Antarctic national operators in the way that they regulate biosecurity, visit frequency, visitor numbers, visitor control, and so on. Now, it's absolutely the case that tourists and national operator staff both provide risks, particularly in terms of environmental damage and carrying non-native propagules, non-native species around with them. And there's good data that shows that. But my view of the Antarctic tourism industry is it's actually pretty well regulated. That doesn't mean there aren't problems. It doesn't mean regulation can't be approved. But in many ways, I think they're ahead of the game. Now, those companies that work in both regions, as far as I'm aware, apply very similar practices in both regions. I think one feature of Arctic tourism that is a little bit different is, I wouldn't quite go as far as saying mass tourism, but in certain circumstances, there are much bigger numbers of tourists involved, and that's much harder to regulate. Now, that could be in the form of much bigger cruise ships. So one of the rules that applies in the Antarctic is the really big cruise ships, while they can sail around, can't land. So whatever the ship itself could produce damage, and throwing waste off it and so on could, but you're not dealing with 5,000 people coming ashore at once. Now, in the Arctic, ships of that size can travel with fewer restrictions at present. And there are obviously parts of the Arctic where much more regular plane connection exists. Very plainly, there are parts of the Arctic with native populations or imported national populations. So there you've got much bigger people movements, much bigger commerce movements and the rest. That brings a whole set of risks that we don't see in the Antarctic. So the challenges overlap. The ways they're regulated in both regions are certainly, again, they overlap, but in some ways they're weaker in the Arctic because there is so much more people movement. So the Arctic could learn lessons from the Antarctic in some respects. in some respects, they're already in place.
Thank you for your presentation and insights regarding the conservation in the Arctic. And I have a question regarding the so-called X factors. Sorry, you have mentioned melting ice and other problems that are of high importance for us, for scientists. And what about the Antarctic? Yes, thank you.
When thinking about any of those issues in the context of the Antarctic, it's very, very easy to underestimate the real practical challenges of any form of major work in the Antarctic. And people have explored it further, if you like, in the context of would the oil industry ever exploit the Antarctic? My slightly candid answer to that is when it becomes economically viable, somebody will, whether we like it or not, because that's the way the world seems to work. But the sheer extent of sea ice around the Antarctic, the sheer size of icebergs, the weather in the 40 to 60 degrees latitude areas, that makes it very, very practical to imagine how you develop a technology that is robust against that. Whether it's a mining technology, it's a geoengineering technology pumping CO2 down into the ocean, whether it's some vast reflector technology reflecting sunlight back up into the sky. I have to say, I mean, this is far, far from any discipline I'm an expert in, so there's no way I can give a really robust factual answer to this. To my mind, the argument that we only have one planet and we shouldn't be interfering with it is one of the strongest ones in my mind. And while people talk about geoengineering, one of the most common talked about aspects of geoengineering relating to climate change is that about pumping CO2 into the deep ocean. It's sort of like you put it a long way away, you can't see it, it can't be doing any harm. We know in the shallow ocean that pumping CO2 into the ocean has extreme effects on the biology, chemistry of the ocean. There's no reason to think it won't do the same if you pump into the deep ocean. So that to do that to an extent that would affect atmospheric CO2 concentrations strikes me as an extremely severe risk, and I'm not seeing anybody being able to discount that risk. And I would seem futility to me to take such a risk with your single planet. And similarly, the argument about putting lots of reflectors up, I don't think anybody has done the if you like, the full environmental cost of making those, maintaining those. There are people who seriously suggested that we should actually be blasting them by rocket up into space. Think about the costs associated with that. Now, it may excite an engineer, theoretically. I cannot see that as a practical solution. And I mean, the bottom line is we know what the problem is. We're pumping too much CO2 into the atmosphere. We actually are getting quite near to knowing how to generate energy without pumping CO2 into the atmosphere to the same extent. That strikes me as a far more sensible alternative to any of these geoengineering solutions.
We often draw parallels from the Arctic and the Antarctic, as we've just done throughout this session. And I think rightly so in terms of governance model science, there's a lot of parallels, obviously those two regions being polar as well. But is there any lessons from Antarctic governance or Antarctic science that could be applied to other regions in the world, to non-polar regions? Or vice versa.
Yeah, my knee-jerk answer to that is one of the most obvious practical ways of applying it, and this does relate directly to conservation, it's almost the simplistic statement that most biology doesn't recognize national boundaries. And for that matter, most climate doesn't recognize national boundaries. So they're a very artificial human construct that we've stuck on the planet. In that Antarctica is an international governed space, it does stand clear from nearly all countries. So there's a lesson in that sense, is that there is a precedent provided by Antarctica for drawing up governance mechanisms that they don't cross boundaries because the boundaries don't exist, but they apply over a much bigger area than you could say in most continents. Now, you can say Australia will be a difference there because that is a single country continent. Most conservation questions, until very recently, and most area protection elements, whatever you call them, have happened within country. until recently, there have been very few national parks that cross boundaries or have parallel national parks on the other side of boundaries. So for me, the idea of international cooperation in larger scale environmental protection is a lesson that Antarctica can point to the rest of the world. I think the Arctic is on a way to doing that. And the Arctic obviously is sovereign governed, and even most of the Arctic Ocean is under some form of sovereign governance. But the level of cooperation between the Arctic states, and now we're in sort of unknown territory with ongoing problems, but until now, that level of cooperation is approaching what goes on in the Antarctic, and the means of communicating between those states is approaching what goes on in the Antarctic. So I think there are distinct possibilities there, yeah.